Alright, so I'm going to make a video trying to explain some trigonometric functions and how to use them and stuff like that. But before I do that, I'm just going to kind of start with a good old right triangle. And before I do that, I'm just going to talk about a triangle. And if you remember anything about a triangle, you remember that the interior angles add up to 180 degrees. So if I took this angle, and I took this angle, and I took this angle, and I added them all up, they would equal 180 degrees. All right, well, in a right triangle, this one takes up 90 of them. Right, so this angle minus 90 means that between this angle and this angle, I only have 90 left. So this angle here and this angle here they are said to be complementary. Complementary. So these two here cannot be more than 90 degrees. So if this one is like, say, 30, then this one's got to be 60. They got to add up to 90 degrees. Okay, so trigonometry, for at least the trigonometric functions, they usually have to do with 90-degree triangles. Okay, at least when they were starting off. Okay, so let's go ahead and name our triangle something pretty easy here. All right, I'm gonna call this triangle. I'm gonna pick some easy letters. Okay, and I have a reason to my letters here. I'll call this one A. I'm gonna call this one B. You might think I'm gonna call this one C, but I'm not. I'm gonna call this one D. Okay, I choose these because the lowercase letters of these look way different than the uppercase letters. So this line segment here is little a. It's opposite of this angle. This line segment is little d, and this line segment is opposite of its angle b. You know what? I'm gonna even change this. I don't want it to be B. I'm going to call it something completely different. I'm going to call it E. Call this E so we don't even get B and D confused. Okay, so I notice how that I distinguished the line segments on the opposite side of the triangle with the same letters of the angles. Okay, so right triangles have three distinct sides. Okay, the most important side or most distinguishable side of a right triangle is called the hypotenuse. Okay, the hypotenuse in our right triangle here, I'm gonna like color it orange. Okay, our hypotenuse is our D1. Right, it is always on the other side of the triangle of the right angle. Okay, in our triangle here, it is opposite of D. Okay, so you need to understand there's some key terms here you need to understand. And opposite is one of those terms. Right? This seems like it's pretty self-explanatory, but opposite means that it is on the other side of the triangle than the angle that we're talking about. So I'm using the D as my reference angle, my 90-degree angle as my reference angle here, and my hypotenuse is opposite of my angle D, meaning that the line segments that make up D aren't even touching my hypotenuse, right? So this line segment D isn't touching the lines that isn't touching angle D. It's opposite of angle D, or line segment D. So line segment D and angle D are opposite each other. Okay? The other two line segments here, the other two legs of the triangle are legs. Okay? I just happen to have a short leg and I happen to have a long leg, and you'll have that in every single 90-degree triangle ever, except when these two angles here, angle A and angle E, are 45 degrees. And then in which case these two legs are the same. Okay, so you'll always have a short leg and a long leg unless this angle here and this angle here are 45 degrees, and then the legs are the same. Okay, but anyway, so either case, these legs here would be what we say adjacent to D, meaning that they help make up D. They touch angle D. They're next to D. So line segment E and line segment A, or side E or side A, are adjacent to D. Right? So E and A are adjacent to D. Okay? So that's another thing that's important to know. Okay? So, but that's the only ever time we're really going to talk about the 90-degree angle, because when we're talking about trigonometry, we're only ever really going to be referencing the one of the other two angles. And so, for instance, say we're talking about this angle E, right? The opposite line segment of angle E is this little guy, angle E. And the adjacent line segment is angle A. And although D is also adjacent to angle E, it's the hypotenuse. And there's only one hypotenuse. And we're going to call it the hypotenuse because the hypotenuse is opposite the 90-degree angle. There is and only will be ever one hypotenuse. So A is the adjacent line segment of E. Okay, so if you find the adjacent line segment, if you find the opposite, you just kind of like look across the triangle, and that's the opposite. And the other one that's not the hypotenuse is the adjacent. Okay, if we're talking about A, right, it's like swapped. Our opposite line segment is this one. It's like A, right? And then our adjacent line segment is the other leg, right? It's E, right? And you can always remember that E, the adjacent line segment, joins the hypotenuse to make up the angle that we're talking about, right? So if A is our reference angle, right, we're talking about A, the opposite one is the one opposite the angle. Okay, it doesn't touch the angle, but the adjacent one does and joins the hypotenuse to make up the angle. Okay, so hopefully, so remember our hypotenuse is the third one. Hypotenuse equals D. Opposite and adjacent, well, it depends. Right, depends. Okay, so so that is, the how all that stuff works. Okay. So let's move on to a new note card. Okay, so now I have a new card here, and I've rewritten my stuff on it. I even color-coded it. All right, so I have D as my right angle still, and my hypotenuse is orange, and it's labeled D for hypotenuse. I guess I could label that H. I'll relabel that as H to make it easier for everybody. Let's make the H and H are big capital H is my hypotenuse, and lowercase h is my length. So that's my hypotenuse angle, or my right angle, and then h is the hypotenuse. And then I have angle E, and then the resulting opposite line segment or leg, and then I have angle A and the opposite line segment A. Okay, so first let's talk about these functions, these trigonometric functions. Okay, they're simply just ratios, right? If I have a right triangle, right, this right triangle is the same angle for every right triangle, okay? And then if I have this angle is the same, then this angle will be the same for that other right triangle, because these have to be, complementary, right? So if this angle is the same, then that angle is the same, right? No matter how big these are or small these are, they're going to be similar triangles. Okay, so the ratio of all of these line segments will be the same. So we can make functions based upon these ratios, based upon the length of these line segments, just like you did when you had like similar triangles and you set up like a ratio of one line segment to the ratio of our line segment equals the length of one line segment, and then equal divided by like your unknown, and then you just like did some cross multiplication, right? This is like kind of like that, but it's like knowing a value for one line segment divided by the other line segment for this angle. Okay, that's a little confusing, I know, but I'll show you here in a second, right? Because for every angle that we know that the line segment lengths are going to be proportional, right? So we figured out all of that stuff, right? So that might be a little confusing because I probably didn't articulate it very well, right? But so I'll just kind of show you. All right, so the first line segment, let's say for instance, I know that for every right triangle, I know that this angle is, some given angle, and this angle is the, 90 minus that angle, right? So, and I know that the ratio of this line segment divided by this line segment are going to be the same. No matter how big or how small the line segments get, the ratio will be the same because they're similar triangles, right? So I can say that the opposite line segment, A divided by, just need like a neutral color here, I'll use red, A divided by H is going to always be some number, right? Will always be some number, right? And it'll be, because H is always going to be bigger than A, right? It's going to be less than 1 for this angle, whatever this angle might be, right? Well, that's a function of this angle, right? If this angle changes, right, this length will change, and so will this hypotenuse change, right? So that value will change. Well, that ratio is called the sine, right? That is the opposite over the thing. We'll just call that for now, we'll call that the sine of A. The sine of this angle A equals the line segment A over the hypotenuse. And then if we wanted to figure out this line segment length over the hypotenuse, right, we could use the sine of E. The sine of E equals equals E divided by H. Right? Because it is the opposite of E divided by H. Okay? It would be opposite over hypotenuse. It's the opposite line segment divided by the hypotenuse. It's the opposite line segment divided by the hypotenuse. Okay? But that's not the only line segment we can use. Right? We can use or that's also not the ratio we can use. Right? If we wanted to figure out like if we wanted to figure out like this angle's adjacent line segment to the hypotenuse, well, there's a ratio for that. That's called the cosine. The cosine of A, right, equals the line segment E divided by H. Right, because it's just this line segment. This is adjacent to it. Right, it's the one that touches A and joins H. It helps make up A and it joins H. Right, divided by the hypotenuse. Okay, and then similarly, we could figure out the adjacent one to E, which is it would be the pink value, unless I've been using burgundy for, the cosine of E equals A, this line segment, A divided by H. Okay? So we're just, it's all relative to the angle that we're talking about in the line segment. All right, so this is how we're figuring all this stuff out. Okay? But we don't always have to use the hypotenuse, right? We can use the adjacent and the opposites of each other, right? That's called the tangent. And so say we're trying to figure out, we're using this angle, right? You can say that the tangent of A, and the tangent is the opposite over the adjacent. So it's going to be that equals A over E, right? And the tangent of E, of angle E, equals E over A. Opposite over adjacent. This is E, it's opposite over adjacent. This is A, it's opposite over adjacent. Okay, that's how all that stuff works. All right. So this is sine, cosine, and tangent. And it jumps around between A and E, and these are all generically, A and E are just generic in nature. They don't have actual real values right now, but they could. Now, finally, they're not going to express these in A and E, right? They don't, like science and math, they don't give you the generic value of A and E. They use a Greek term called theta. Theta. And theta looks like this, right? So they'll say, hey, this is theta, right? So the cosine of theta equals A over H. Or maybe this will be theta. And they'll move theta around, and you got to be like, okay, theta's here, so this line segment is the opposite, and this line segment is the adjacent. Or like, okay, theta's here, so this line segment is the adjacent, or is the opposite, and this line segment is the adjacent. But the hypotenuse will always be opposite the 90-degree angle. Okay? I'll go ahead and pause it. From here on out, will just be some examples of how to like rearrange stuff and solve for stuff and things like that. Okay, so here is a basic, simple one. Here is our angle. I'll use this one. I'm only going to use one pen here to make it, one color to make it simple. Here's our angle theta. Here's our 90-degree angle. So this is our hypotenuse, right? This, in reference to theta, that is our opposite, and this is our adjacent. Right, so that might help you if you label everything first. Right, so you remember that our sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And tangent of theta is opposite over adjacent. Okay, so you can do something like this here. Maybe I'll zoom out a little so you can see all the calculator. All right, so sine of theta equals the opposite, which is 48 over 60, right? So 48 60ths, and press sine is, wait a minute, that's not right, 48 60ths. Sine is that. That is the sine. I'm just going to put it like, I'm going to keep it as 48 60ths. Right? But that's the sine of that value. Right? So cosine is 36 60ths. Right? So if I go with 36 60ths and push cosine, that is that value. And surprisingly enough, if I add 48 60ths to it, never mind, I'm going to disregard that. All right, so we're going to go ahead and go, the tangent is opposite, which is 48 60ths, and that's going to be 4/5. Oh, and then we're going to take the tangent of that. Oops, take the tangent of that, and it equals that. Okay, but it's still just 48 opposite 48 36. Oops, I did that wrong. So it's opposite over adjacent, which is 48 36, and take the tangent of that, and that is, so 48 36. Take the tangent of that, and that's the tangent of 48 36. Okay, I got someone knocking. Hold on. Okay, so here is another one. And we could use Pythagorean's theorem to figure out the long side, but I'm going to show you how to use trigonometry to figure out the long side of this. Okay, so we know that this angle theta is between the, this is the opposite. This is the opposite that I need to know, and this is the adjacent, and this is the hypotenuse. Okay, so I need to figure out this angle theta. All right, so I'm going to write out the definition of this angle in terms of trigonometric functions. Right, so I'm going to say that the cosine, because I know everything except this angle. Right, so the cosine of theta equals adjacent, which is 4, divided by hypotenuse, which is 9. Okay, so I know that the cosine of theta equals 4/9. Okay, so I'm going to solve for theta by taking the arc cosine. The arc cosine of 4/9 equals theta. Right, so this is how you do that on a calculator. Okay, so I do 4/9. Right, and I do the second. I press this little arc cosine button, And I know that this angle is 63.6 degrees. So theta equals 63.6 degrees. All right, so if I want to figure out what this line segment is, I will kind of like put this in terms of like the opposite in terms of the hypotenuse. So the sine of theta, so the sine of theta equals the opposite over my hypotenuse, which is 9. I'm going to erase this, maybe make it a bigger, and saying the sine of 63.6 equals opposite over 9th. I need to solve for opposite. So I'm going to take this 9 and put it over here. And that'll change this into this. So that 9 times the sine of 63.6 equals my opposite. And that should make sense because the sine and the cosine is always going to be smaller than 1. Right? So multiplying anything by something that's less than 1 is going to result in something smaller than the thing I'm multiplying it by. Right? So what I mean by is if I take 63.6 and I press the sign, it is a value less than 1. Right? This, if you want to say this is a percentage sign, this is like 89.5%. Right? And if I multiply this by 9, it's going to make that value smaller. Right? So that means that like this is like 8-ish, like 8.06-ish. Okay? So this is 8.06. All right? But anyway, I figured out that this was 63.6 degrees, right? So I can just say that the 63.6 sine is 0.896. Usually you want to go 3 digits, rounding to the nearest hundredth. So take 63.6 and press the cosine. That's going to be, well, we already figured it out. That's the cosine of 4/9, which is 0.445, 0.445, and then the tangent of theta. So 63.6 degrees is our theta, and the tangent of that is 2.01, 2.01. All right, so something to note, okay? Tangent will be positive if your opposite line segment is longer than your adjacent line segment. I'm sorry, not positive, excuse me. Tangent will be greater than 1 if your opposite line segment is longer than your adjacent line segment. Okay, if it's less than your, like for this one, if your opposite line segment is shorter than your adjacent line segment, then it's not going to be. Okay, so that's something to know. Okay, so let's see what's on the back page of this examples here. These examples. All right, so these are just more examples for solving for x. Okay, so we have, like, we'll do this one here. Right, identify your hypotenuse. There's your right triangle, so that's your hypotenuse. In reference to your angle theta, that's your angle theta. So this is your opposite, and this is your adjacent. Okay, so you need to figure out what you're trying to solve for. So you're trying to solve for your adjacent. Right? So to solve for you need to use the cosine. So you go the cosine of 55 point. Well, first you need to find the hypotenuse. You don't know the hypotenuse. Right. in order to find the cosine, you need to know the hypotenuse, or you can use the tangent. You can do that too. All right, we'll just use the tangent. So we know the opposite, and we need to figure out the adjacent. So we use the tangent. Okay, it has both opposite and adjacent in it, so we use the tangent, because tangent theta equals opposite over adjacent. So we write out what we know in terms of the givens. So the tangent of 55 degrees equals opposite is a 29 degrees divided by x. Okay, now we rearrange the equation to solve for x. When this is on the bottom, these two terms just swap. When x is on the bottom, these two terms just swap. All right, so x equals 29 degrees divided by tangent of 55. All right, so to put this into the equation, you go 29 divided by, all right, so 29 divided by, now you got to put 55 and then press tangent equals, now x equals 20.31. 20.31. That's how you do that one. Okay, we'll do another one. Here's this one here. Okay. This one here, I have my theta. I try to figure out my hypotenuse, and I'm giving the opposite. Okay, so what function has opposite and hypotenuse in it? That's sine. Sine of theta equals opposite over hypotenuse. Plug in what I know. Sine of 15 degrees equals opposite divided by hypotenuse. H is on the bottom, which is my x value. So I gotta swap the two. X equals 16 degrees divided by the sine of 15. Okay, that makes sense because whenever I divide something by less than 1, it'll make it bigger. Right, so 16 degrees divided by 15 sine equals 61.8. Equals 61.8. Right, so this is 61.8 degrees. Okay, so here's an opposite and adjacent, so that's tangent of theta. Here is this one is going to be a adjacent and a hypotenuse, so that's going to be a cosine. You're going to use cosine of theta. This one is another cosine of theta because it's adjacent and hypotenuse. This one's an opposite and adjacent, so it's a tangent, right? So you kind of see how everything's going. Okay, hope this helped out for you guys. Have a great day.